Welcome back, students. Today we will learn differentiation of the vector fields. Already we have learned in last class about vector fields, scalar fields, and differentiation of the scalar field, that is gradient. In this class we are going to cover these topics: divergence, curl, second order differentiation of the fields. Divergence is, as it sounds, how much field or its flux is coming out of the point of interest. Let me say this is the point of interest, then how much field is coming out or flux. That quantity we are going to define it later. Then curl is something how a field is rotating near a point of interest. Let us formally define divergence in Cartesian coordinates. It can be defined in other coordinate systems also, but right now we are interested only in Cartesian coordinate system, that is XYZ. This is the region of space in which we have defined vector field. Any vector field can be expressed using components. This is the vector field here, as it is shown here. It has x component, then it has a component in y direction, fy, component in z direction. Then divergence is denoted like this, or using del operator I can write this as divergence as shown here, and it is defined by take the x partial derivative of the x component only, then similarly y component only, then z component of the field with respect to z, then you add all these three derivatives. Observe here no ijk's have come, only numbers. Therefore ultimately you will get just a number at any point or scalar at any point, no direction. Therefore after taking divergence of a vector field you will have a scalar field. Now to give a geometrical interpretation or meaning, I have to define something called flux. Let us say I want to calculate at this point divergence. Then electric field is coming out of this small patch ds. You can define a vector which is normal to this small patch of the surface. Then you take field defined somewhere in this region and take dot product, that f dot ds is called as small flux through this small area. Total flux, if you want to define for a bigger surface like this is a cube which has 6 surfaces. Now if you want to define total flux coming out of this side surfaces, then you have to do this, you have to take integration. Total flux will be defined by integration over the closed surface. Now geometrical meaning of the divergence. Divergence at any point represents total flux coming out of the surface of a cube. It can be any shape, not only cube, any closed surface. But let us stick to cube. Divergence at any point represents total flux coming out of the surface of a cube of very small volume. Why small? Because I am interested only in this point how field is varying. Therefore, if we take larger or bigger cubes, then it takes account of the vector set very far away points. But I am interested only in small region around this point. It is defined in calculus sense, then you make that cube volume go to 0. Okay, in that sense we have to calculate the divergence. Once again I will repeat, divergence at any point represents total flux coming out of surface of a cube of very small volume. This is the geometrical meaning. Now intuitively let us grasp using our intuition. What is the divergence at this point? You ask this question and we will see here it is coming out. If you say here also it is coming out, therefore something it should be coming out of this small surface, small cube. Therefore, you should have all the partial derivatives greater than 0. Hence, our divergence of the vector field here, it must be greater than 0 or positive. Here, everything is coming in field. Therefore, if you consider at this point, all the derivatives are negative. Therefore, divergence is negative here. In fluid dynamics, these are called sink, these are called sources. Here, what comes in, that is leaving also. Therefore, no variation in the field. Hence, all the derivatives are 0. Therefore, divergence is 0. Next, we will define solenoidal field. It's also an important concept. A vector field has zero divergence at all points in a region. Then we say it is a solenoidal field. If you consider this is the region of the space, then there are field defined. Field is not zero at every point, but if you calculate divergence at any point in this region, then that will be 0. Div of f is 0 at all these regions. Then we will say that field is solenoidal in this region. A good example is magnetic field. Since we know that divergence of B is 0 at all points. This is the second Maxwell equation. Later you will learn. Therefore, magnetic field is always solenoidal. Let us practice this concept of divergence with few numerical problems. So, suppose I want to calculate field, divergence of the field. Field is given by f is equal to 3x I plus 4y j plus 9 zk. Then divergence of f is given by dou fx by dou x plus dou by dou y of fy plus dou fz divided by dou z, and you will have fx. Here fx is 3x, x component 3x, therefore after differentiation you will get 3 from this, and similarly 4 from this, and here 9z, therefore you will get 9, therefore 13, that will become 16, and since 16 is greater than 0, that is at every point divergence is positive. Divergence is positive. We will have another problem. Calculate the divergence of field f is equal to 3 times position vector r. That field at every point, it is nothing but 3 times the position vector. Calculate its divergence. Divergence of f is dou. This vector can be written also, it can be written as 3 times xi plus 3 times yj plus 3 times zk. Therefore, dou fx by dou x, dou fy by dou y, dou f z by dou z is equal to, and this number here 3x, therefore 3 plus 3 plus 3 is 9. Another some interesting example where it varies with respect to point. Divergence also varies with point to point. Let us consider f is equal to 3x square plus 2y plus 9z cube. All the we will have, since it is a vector field, we must have ijk's. Okay, div f is equal to derivative of this x component, that will be 6x, derivative of this y component 2y, that will be 2, derivative of this 9z cube, that will be 27z square. Now as x and y point varies, x and y z also vary, therefore divergence f is also a function of point, therefore it is a scalar field. If you want to calculate this divergence at any particular point, say at point x is equal to 1, y is equal to 0, z is equal to 2, then div f at this point will become 6 plus 2, 27 into 4, that is 116. Now we will learn another kind of differentiation defined for vector field. Earlier we have learned one kind of differentiation called divergence, which applies to vector field. Another kind of differentiation also we can define. Whenever I say differentiation, they measure some kind of change with respect to space. How much if I move, something will change like that. Any vector field in Cartesian form can be defined like this. X component of that field means something which multiplies by I. Fy, that is the y component, something which multiplies j cap. Z component which multiplies k cap unit vectors. Observe that this fx can be a function of x, y, z also. Not only necessarily not only of x. Okay. For example, fx can be like this: x square y z, or it may be y sin z, like that. Here x won't come into picture. Therefore, fx may depend on x or y or z. Similarly, y and z components. Now we will define how to compute curl of the field in Cartesian coordinates. That is defined using, it is nothing but cross, you can think this as cross product between del operator and field. And any cross product is defined using determinant. This is not modulus, be careful. Many students, they will confuse this with modulus. No, it is determinant here. On the top row, ijk vectors, this is partial derivative with respect to x, partial derivative with respect to y, partial this one in the second row, and then x component of the field, y component of the field, z component of the field. Remember, always differentiation should come first. While expanding this one, you should remember that always differentiation should come first. If you do that, then it will be, as I have shown here, it will be dou fz by dou y minus dou fy by dou z I cap. Similarly, whenever you are learning vector calculus, you must have paper and pen with you. After taking curl, we get another vector field. See, ijk's have come, therefore whatever I am getting after taking curl, that will be a vector field. Now we will consider geometrical meaning or abstract definition of the curl. This is very difficult to assimilate in one watching, but you can have repeated watching, or you can go to other good websites also, or YouTube videos. How to define curl independent of coordinates? That if you consider, see, whenever you have a field, vector field defined over in this region, you consider where you want to consider the calculate the curl. At that point, you consider a surface. For example, a small cube. Okay, if you want to compute here, then you consider a small cube, and there you have a normal to this surface. Cube have 6 side surfaces, and consider one top surface, let me say. Then you draw that normal. Then you have defined field over at that point. Okay, this is the field vector. Then you can take this normal vector is proportional to the area of this surface, ds vector. This is ds vector. Then you can, anyway you have two vectors now, you can define cross product. Okay, that will be like this. Then you make this volume of this small cube go to 0, because I want to consider something at this point only, not over something extended region. you make that volume go to 0, and while doing so always you first construct this cross product, then you make it divided by 1 by volume and do the surface integration not only on this surface, all the 6 surfaces. Similarly, this now I have shown as volume goes to 0, then you have curl vector defined here. Okay, this is the curl vector at that point. As the volume goes, it will go to some limit, this one, and after dividing by volume, that will go to some limiting vector, and that limiting vector is called curl. This can be defined in another way also, which is very useful. If you want to calculate out that curl vector in any direction, n cap, it is a normal vector, a unit normal vector, then you have to do this one. Take the field, then take the dot product with that. This is not now surface vector, this is the length vector. It should have been dl vector, and you should consider a curve, closed curve, in a plane perpendicular to this unit vector n cap, and you take this line integral, divide by the area bounded by that curve, this one area, and that will go to the limit. That will be the component of this curl vector along that n cap direction. Therefore, this quantity is called circulation. Therefore, curl is a measure of circulation per unit area. This is the geometrical definition. Curl is the circulation per unit area. After defining geometrically what curl means, uh, curl free field or irrotational field we are going to consider. If curl of a vector field is 0 at every point in a region R, then we say that it is a curl free field or irrotational field. If this is the region, and at every point if you calculate curl, vector field may not be 0 at every point, but curl will be 0 at every point, then we say that as irrotational field or curl free field. Example, electrostatic field. Now let us define a del square operator or Laplacian operator using second order derivatives. This operator is called Laplacian operator, denoted by this del square, and defined in Cartesian coordinates. You have to differentiate with respect to all the spatial variable twice, then add. That is the meaning of this one. Note, the Laplacian can act on scalar function. It will give back you another scalar function. Laplacian can act also on a vector field or vector function, gives back you vector field. Therefore, Laplacian can define for scalar field and also for vector field. Very important, you should note it, because in electromagnetism we will operate del square both on scalar field and vector field like electric field or magnetic field. We will note this thing with two problems. Here f is a scalar field, no ij case, x square plus y cube z square. You can have your supplementary notes along with this video, it will be beneficial. And here dou square by dou x square operates on f, dou square by dou y square operates on f, plus dou square by dou z square operated on f. If you substitute f from this one, then you will get del square f is equal to 2 plus 6yz square plus 2y cube. Here no ij case, therefore this is also a scalar field. Then here it is a vector field and we have to operate Laplacian. While operating, we will note that this is a scalar field. Therefore, in Cartesian coordinates, it is quite easy. When del square operates on any vector A, then you have to operate del square on its x component. Then whole thing should be multiplied by I, plus similarly it goes on. Del square operates on AY. Whole thing should be multiplied by j cap. Then del square AZ, whole thing multiplied by k, ijk. This if you do, then 6x square plus y square. Del square v is equal to, if you do all these things, you will get 6x square xy square plus 2x cube into I. Similarly it goes on. You practice. Next we will note some important properties. Curl can be defined for any vector field. Then you will have a scalar field here. First you take gradient. Therefore once you have differentiated, then you define curl for that resulting vector field, and that will be always 0. That means at all points, if you take curl of a gradient for any scalar field, that will be 0. Okay, that means in another word, gradient of any scalar field is irrotational or curlless. Let phi be a scalar field. Proof goes like this. Let phi be a scalar field and then take gradient. You know now how to take a gradient. Then use those components of the gradient as components for the curl, not components for the, that you should write in third row. Then you expand it. By doing so, this one you got it like this. Here one thing we will know, we will note, if phi is a continuous function, then taking differentiation in which order is not important. First you can take derivative with respect to y, and then you take derivative with respect to x. That is same as taking first with x then with y. Therefore, by using this property, we can show that curl of gradient phi is always 0. Similarly, another property, when you take curl of vector field, then you take divergence of that resulting vector field. Divergence of curl V, that is also 0. Using same property of mixed derivatives, we can show that it is also 0. That you have to practice all these computing, all these derivatives, you must master. Then another important property which we will be going to use in our course is this one, divergence of gradient. That means any scalar field, if you take first gradient then divergence, this is also second order differentiation, that is equivalent to taking directly operating Laplacian on that field. That is left as an exercise. Another important property which we are going to use in proving electromagnetic fields, when they are varying, they propagate like waves. In that proof also we will use this property. Curl of curl. Curl is a vector field. Therefore, once again we can take curl. Curl of curl, that is gradient of the divergence of that vector field minus directly operating Laplacian on vector field. Therefore, now you know that curl, divergence, Laplacian, all those differentiation of the fields are very important in knowing to know the electromagnetic